If you think about it, the inside of your body is kind of like a huge, incredibly complex symphony. You've got countless reactions and processes, all happening at once, all playing in perfect harmony. But who's conducting this thing? What's the maestro calling the shots? Well, the answer is going to surprise you. It's not some big, complex organ. It's an invisible force we're going to explore today. And right at the heart of this entire biological orchestra is a single, deceptively simple number, a value so fundamental it literally dictates the rhythm and the tempo of life itself. That's right, this one little value, a measure of something we call pH, it governs everything. It tells proteins how to fold into their crazy, intricate shapes. It tells enzymes when to spark the reactions that keep you alive. It's how your entire body stays in this delicate, perfect balance. Honestly, understanding pH is like learning to read the sheet music for the symphony of life. So let's dive in and see what this is all about. So what is this molecular conductor actually saying? What language does it even use? Well, it all comes down to a simple measurement on a very, very powerful scale. Okay, so scientifically, pH is just a measure of how many hydrogen ions are floating around in a solution. The scale usually goes from 0 to 14. Right in the middle, at 7, that's neutral. Think pure water. Anything below 7 we call acidic. Anything above 7 is alkaline or basic. It's pretty straightforward. The more hydrogen ions you have, the lower the pH number, and the more acidic the solution is. Now, here's what makes this so incredibly powerful. The pH scale isn't linear, like a ruler. It's logarithmic. That means a change of just one single unit, say from 6 to 5, is actually a massive 10-fold increase in acidity. So think about this. The acid in your stomach is around pH 1.6, while your blood is about 7.4. That might not sound like a huge gap, but it means your stomach acid is literally millions of times more acidic than your blood. It's an incredible range. Okay, so if pH is our conductor, then what are the instruments in the symphony? Well, they're the essential building blocks of life. We're talking proteins and DNA, and pH is the master sculptor that gives them the exact shape they need to work. And you can see just how critical that shape is right here. On the left, when the pH is just right, that protein is folded perfectly, and the DNA is in its stable double helix. They are tuned up and ready to play their part. But look at the right. At the wrong pH, too high or too low, the delicate electrical charges holding them together get all messed up. The protein completely unravels, we call that denaturing, and the DNA strands just fall apart. The instruments are basically broken and the whole symphony just grinds to a halt. Now, every great orchestra needs its star musicians, right? The players who really make things happen. In our cells, those are the enzymes. They are the catalysts that make life's reactions happen at incredible speeds. And their performance is super, super sensitive to our conductor's direction, the pH. Just like a guitarist has to be perfectly in tune, every single enzyme has an optimum pH. It's the super narrow range where its activity is at an absolute peak. You can see it in this classic bell curve. If the pH strays just a little bit from that sweet spot, the enzyme's performance just plummets. It's that precise. Let's look at a fantastic real-world example of this. Here we've got two different enzymes from your digestive system. On the left is pepsin. It lives in the super acidic environment of your stomach, and it loves it there. Its sweet spot is a pH of about 1.6. But on the right, you have another enzyme that works in your small intestine, where things are much more neutral, and its peak performance is way up around a pH of 7.5. It's just a beautiful look at specialization. Each musician is perfectly tuned for its specific section of the orchestra. So, how does pH actually have this much control? What's the secret? It all comes down to electrical charge. See, the active site of an enzyme, the part that does all the work, has specific amino acids. The surrounding pH determines whether these little guys gain or lose a proton, which changes their charge. And that change in charge acts like a tiny molecular switch, flipping the enzyme's function either on or off. It's that simple. Okay, so we've seen how pH tunes the individual instruments and directs the key musicians. But now, let's zoom out. Let's see how our maestro, pH, coordinates these incredibly complex processes across the entire organism to create this beautiful, system-wide harmony. And there is no better example of this than something called the Bohr effect. It is a truly elegant, beautiful system for delivering oxygen around your body. It shows the whole orchestra playing together in this perfect, dynamic rhythm, all conducted by these tiny little shifts in pH. Okay, so here's how it works. When you take a deep breath, the pH in your lungs is a little bit higher. This signals hemoglobin in your red blood cells to grab onto oxygen and hold it tight. Then, as that blood rushes out to your hardworking muscles, which are busy producing CO2 and other acids, the pH in that area drops. And that drop is the cue. It's the signal for hemoglobin to change its shape and release that oxygen, delivering it right where it's needed most. It is absolutely brilliant. But wait a minute. With all these acids being made all the time, how does the whole system not just spiral out of control and become too acidic? Well, this is where the unsung heroes of the story come in: biological buffers. You can think of them like the expert sound technicians at a concert, constantly working in the background, tweaking the levels to resist big changes and keep everything perfectly in tune. And the most important one in our blood is the bicarbonate buffer system. Now, I know what you're thinking. You see an equation and your eyes glaze over. Don't worry about the math here. Just think of this as the simple rulebook that these buffer technicians follow. It's the precise formula that lets them soak up any excess acid or base, making sure that the symphony of life always maintains its perfect pitch. So far, we've seen this incredible system of perfect control, of perfect harmony. But for our finale, let's take a look at what happens when the conductor loses control, when the pH shifts and the whole orchestra just descends into chaos. So what this all leads to is a constant, critical balancing act. Your blood has to be kept in an unbelievably narrow pH range, between 7.35 and 7.45. I mean, that's it. If it dips below that, it's a condition called acidosis. If it goes above, it's alkalosis. And both of these can totally disrupt your metabolism and quickly become life-threatening. A really serious example is how untreated diabetes can lead to a severe and sometimes fatal form of acidosis. It really makes you think, doesn't it? We always focus on the big things, the heart, the brain, the lungs. But what if the most powerful, most critical force keeping us alive isn't a thing at all? What if it's just a simple, exquisite, and profoundly important balance? Because in the end, that's what pH is. It's not just some static number in the background of a chemistry textbook. It is the molecular maestro. It's an active, dynamic force that sculpts our molecules, directs our enzymes, and maintains the delicate harmony of our entire system. This exquisite balance, constantly guarded by the quiet work of buffers, that's not just chemistry. That is the sound of the symphony of life itself.